Let's imagine a person standing on a railway platform. A person is standing on a railway platform and a train is approaching to the platform. And the train is blowing the horn and it is coming towards the observer or the listener on the railway platform. The question is how the observer will listen to the horn or the pitch or the frequency that is being blown by the engine. You know, as the train comes towards the observer, the pitch is much bigger, pretty bigger. The frequency is higher. And as the train recedes the observer, the frequency becomes lower. As it is approaching the observer, it comes with frequency which the observer seems to be it is much more than the actual one. And as it recedes, the observer listens to the frequency that it has reduced than the actual value. For example, a train is blowing a horn at a frequency of 540 Hertz. It is just moving at 540 Hertz frequency horn only. But for a person on the platform, as it is receding, he just perceives a frequency which is bigger than the actual value, maybe 560 Hertz. And as the train recedes, he perceives the frequency with a value lesser than the actual value, maybe 520 Hertz. But actually, what is the value of the frequency? 540. This phenomenon is called as Doppler's effect. The actual frequency is 540 in this case. The person perceives at 560 Hertz as it is approaching, as the train is approaching him. This 560 is called as apparent frequency. See, here we have got two things to note down. One is the actual frequency of the source. Actual frequency of the source. The source could be anything, maybe a whistling train or a sirening ambulance or a sirening fire engine, whatever it is. This is denoted in this chapter as F Hertz. And the person do not actually listen this actual frequency. He always perceives at different frequency. That is called as apparent frequency. Use the word apparent frequency, and this is heard by the listener, and this is denoted as F dash. So we are having two types of frequencies. Actual frequency is generated by the source, but apparent frequency is perceived by the listener. So in order to understand the Doppler's effect can be defined as the apparent frequency as perceived by a listener may be moving, he may be moving or he may be stationary. That means the source and the listener are in relative motion. When the source and the listener are in relative motion. Here I want to tell you what is meant by relative motion. The observer is at rest and the source is coming towards. Though he is at rest, in comparison to the source and the observer, it's a relative motion. In this relative motion, we say that the observer is at rest, the source is moving, or the source may be at rest, the observer, he may be coming towards the source, or he may be going away from the source, or the source and the observer, both are in relative motion now, both of them are coming towards each other, or the source and the observer are again in relative motion because both of them are going farther away, far away and far away. So any of these type of motion, study of motion of one with respect to other, the source with respect to the listener, is the relative motion. So remember how to define Doppler's effect. Doppler's effect can be defined as the change in the apparent frequency the change in the apparent frequency when the source and the listener or the observer are in relative motion is called Doppler's effect. I repeat once again, the change in the apparent frequency. When do this change? It is not actual, it is apparent. That means the meaning of the word apparent means something which is not true. The train is coming with 540 Hertz horn only, frequency of the horn is 540. But you get it at 560 Hertz as the train is approaching you. And after the train leaves you, that is, it recedes you, you will not get that 540 again or 560, you will see it at 520 Hertz or you will listen at 520 Hertz. So this 540 is actual, 560 and 520 are apparent frequency. The change in the value of the apparent frequency when the source and the observer are in relative motion is called Doppler's effect. Are you understanding the definition of Doppler's effect? I repeat once again, the change in the value of the apparent frequency when the source and the observer are in relative motion. This is called as Doppler's effect. Now, to understand Doppler's effect, we need to understand some basics. Basic number one is a wave moves out like this. It moves with a velocity v, and this v is given by f lambda. We are familiar with this equation. What is the equation of the velocity of wave? F lambda. So I write basic number one, v is equal to f lambda. If v is equal to f lambda, what is f? If v is equal to f lambda, what is f? F lambda is equal to v. Therefore, f equals v by lambda. And sometimes we also write the value of lambda. What is lambda? You can tell me. V by f. E by f. So these three things you keep in your mind. This is basic number one in understanding Doppler's effect. Though this is very simple thing, but you should make a note of it. Now, second basic. Now listen to me. A particle moves at a velocity of 3 meters per second. And it covers a distance of 3 meters. So what is the time it has taken? 1 second. A particle moves with a velocity of 3 meters per second and covers 3 meters. So what is the time it takes to cover this 3 meters? 1 second. So here we know that velocity is distance into time. If t equals 1 second, as in the example I have given, then velocity becomes equal to distance traveled by the body. You can replace the velocity factor v by the distance the wave has covered. Whenever time of motion is for 1 second. So keep this also in your mind. Okay. Point number 3. I said a train approaching you from the signal to the platform. When it blows the horn, you listen to the horn with the same frequency or with increased frequency? Increased frequency. And as the train recedes you, you listen to the horn with the same frequency or decreased frequency? Decreased frequency. Why should it be? The reason is, now I say 2 words. Implies towards implies lambda is small. Lambda is small. This implies frequency. Frequency is large. What is the meaning of this? When the source and the observer are coming towards each other, or maybe any one of them be at rest, but still one is coming close to the other, or maybe both of them are coming close together. That means both are moving towards, or at least one of them is moving towards. Either the source is moving towards the observer, or observer is moving towards the source, or both of them are moving towards themselves. In any of these situations, you know, the waves will have smaller wavelengths, and therefore their frequency is large. When I say away from each other, what is the meaning? Lambda is large. Therefore frequency is small. You know, frequency is inversely proportional to wavelength. You should be knowing that. Note that frequency is inversely proportional to wavelength. Now let's take the example of a car moving very fastly, blowing horn, honking the horn. It just passes in front of you. Now how the sound you perceive? You get the frequency bigger as it comes to you, and as it goes, just goes out of your sight, or rather goes in front of you, or it precedes you. How the horn you listen? You listen at a decreased pitch. As it is approaching you, you listen with increased pitch, and as it precedes you, you listen with decreased pitch. It is because, now let's take that this is the car that is coming towards you. Okay? Don't ask me which model, which brand and all, some car. Now you are here. Or let me say, you are here. Now, the waves in this region are much closer. Now the car has blown the horn. Now look at each one of them is a wave, and the distance between each wave or the wavelength is lambda. Now you see lambda is small here, so frequency is large. Now the car as it passes on through you, now the waves will be like this. Now here in this region you see lambda is larger, so frequency is small. This is high frequency area and this is low frequency area. So you are there and car is coming towards you. The waves are a bit compressed here. As the source is coming towards the observer, this is the source, this is the observer. Now it is coming towards the observer. What happens to the waves? Sound waves, they get compressed. If the source makes sound, generates some amount of frequency and it is coming towards the observer, then the waves will have smaller wavelengths. Therefore the frequency in that particular region is high. And as the car recedes, now the waves have more wavelengths. That means frequency becomes low. So that is why you now perceive the sound with different frequency. This is all what is Dopplers effect. Okay? So I have told you what is the definition of Dopplers effect, and now we will discuss about the situations that we come across by understanding the Dopplers effect. Three important situations. Three important situations. We study Doppler's effect under three important situations, or under three cases. One is the observer is at rest, the source is coming towards the observer. observer is at rest, the source is coming towards the observer. So this is case number 1. Observer at rest. The source moves towards observer. The moving source, the stationary observer. Case number 2 is the vice versa of this. Observer is moving. The source is at rest. Observer is moving. The source is at rest. Case number 3 is both observer and source are in relative motion. Or I say both observer and source are moving. What are the 3 important situations in Doppler's effect? The observer is at rest, source is in motion. Second, the source is at rest, the observer is in motion. When I say in motion, the observer may be coming towards the source or may be going away from the source. And third case is both the source and the observer are in relative motion. They may be moving towards themselves or they may be moving away from each other. We have to derive mathematical expression for each of these 3, and that's an important question for your exam according to the new syllabus. Okay? Now, Doppler effect studied under first situation. You may just write down this derivation. Doppler effect, when the observer is at rest, the source moves towards the observer. I'll consider a source and an observer. Let S be the source and O be the observer. That source can be anything, maybe a engine or a fire engine or a car, whatever it is, which is generating, which is emanating frequency. That means which is sending out frequency. Now at the beginning, at the instant, both the source and the observer are stationary. At the beginning of this situation. Now imagine a train is standing at a signal point and an observer is on railway platform 1 kilometer from the signal. The train is now standing, it is stationary. Now it blows the horn so that it wants to move. When it blows the horn, the waves will start moving. Waves will start moving towards and reaches the observer. Okay. Let V be the velocity of the wave that reaches the observer. You imagine now the engine has blown the horn. That horn should reach you that you are in 1 kilometer in the railway station. So the wave has now traveled 1 kilometer distance. So it has started moving. Let V be the velocity of the wave. Okay. Now this distance, I write here. Let S be a source and O be the listener. O be the listener. Let F be the actual frequency of the sound. means being given out, emanated from S. Let the sound travel with a velocity v. With a velocity v. By covering a distance of the sound travel with a velocity v meter per second, by covering a distance v meter. So, what is the distance from S to O? V meters. S to O, the distance is v meters. And what is the speed with which the wave is coming? V meters per second. We have just assumed that the distance between S to O, that is source to observer, is v meters. And the sound is coming with a velocity v meters per second. Therefore, what is the value of t? T equals 1 second. That is the sound reaches the observer in 1 second. In 1 second. Now, I mark the wavelength of the wave. Let lambda be the wavelength. Let lambda be the wavelength. And how many waves are contained in S2O? F number of waves, because F is the frequency. Frequency is the number of waves per second. Wave takes 1 second time to reach O. And what is the frequency of this wave? F. That means F number of waves are contained in the region S2O. Now I use this formula. We know that lambda is equal to V by F. If t is equal to 1 second, whenever this type of situation we can replace V by T. The distance it has travelled is S4 by F. What is the distance d? V is denoted by S4. So lambda is this value. This value is the entire length divided by number of such cycles, such waves. The entire length of S4 divided by the frequency of the wave gives the wavelength. I have just used the fundamental formula. Fundamental formula for lambda is V by F. And whenever t is 1 second, E equals t. Here the distance travelled by the wave is S4. So I have just replaced V by S4. Okay. Now, let us consider the situation. Now actually, what? The source has started moving towards the observer. Look at this. This is the observer. He is on the railway platform. The engine was at rest here. It got the signal. It blew the horn. And the horn reached you in 1 second. And in 1 second time, it has already traveled some distance. It has blown the horn and it has started moving. So, how much time you take to listen to that sound? 1 second. In 1 second, the train has moved, it has started coming towards you. So let it come to this new position. Yes, let's call it as S dash. And you are here now. You are here. I said, when the source moves towards the observer, what case it is? Towards case or away case? Towards case. In towards case, frequency is more or less? More. More. Lambda is less or more? Less. So all these waves from S to O must be now accommodated within S dash to O. What is the frequency? 1, 2, 3, 4, 5, 6, 7, 8. So all these 8 waves. 1, 2, 3, 4, 5, 6, 7, 8. Now look at this. Therefore, their wavelength has become lesser now. This is lambda dash. And the source has moved from S to S dash with a velocity, let's say Vs. What is Vs? Velocity of the source. So now I write, let the source move from S to S dash, S to S dash in 1 second with a velocity is with the velocity is. Since the source moves towards lambda decreases, wavelength decreases, and the new wavelength is given by, and let the new wavelength be, given by lambda dash. Okay, now use again the fundamental formula for lambda. Lambda is d by f. Here also velocity has been occurred in 1 second time. So here what is the distance left over? S dash go divided by f. The same f here also. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. F remains the same. Only wavelength now decreases in the allotted space. So lambda dash equals S dash 4 divided by S. From the figure, S dash 4 is, if you geometrically observe S dash 4 is SO minus SS dash. Can you see that? S dash 4 is S4 minus SS dash. Can you make it out? Yes. Therefore, lambda dash equals S4 minus SS dash divided by F. I have replaced S dash O by its actual value, S4 minus SS dash divided by S. Or lambda dash equals S4. S4 is the entire length, that is d meters. Therefore, S4 is the distance. Distance can be replaced by velocity. SS dash is the distance. Now it has to be replaced by Vs divided by F. So lambda dash is equal to d minus Vs divided by F. If F dash is the apparent frequency, what is the basic formula for frequency? F equals d by lambda. Or I write F dash equals d by lambda dash now. And now calculating the value of the apparent frequency when the train or when the inching comes towards the observer, and that is given by f dash equals v by lambda dash. But we know what is the value of lambda dash now. So this implies f dash equals v divided by lambda dash, that is v minus vs by f, or f dash equals, what do you write this, v minus vs f dash equals v by v minus vs. So many hertz. This is the Dopplers formula for the source moving towards a stationary observer. The stationary observer will perceive the frequency with a value, how much? V. What is V? V is velocity of sound. The sound takes to reach from S to O in 1 second, where V is the velocity of sound, Vs is the velocity of the source. Here, V is the velocity of sound, or the distance the wave has travelled from S to O. Velocity is same as distance in this case when t equals 1. V is velocity of sound. Did you understand why is V velocity of sound? Because as the train blows the horn, the sound reaches him in 1 second. So that is velocity of sound. And what is this Vs? It is the velocity with which the engine moves from S to S dash. It is velocity of source. It has started moving from S to S dash. Actually, what is the situation when the source comes to S dash? It won't stop here, it keeps further moving. I have taken 1 point, S dash. When the source comes to S dash, the waves get compressed. The amplitude or wavelength becomes smaller. So, all these waves now have to be accommodated within this region now. And that's why you get the new wavelength, which is V minus Vs by F, and substituting the formula for the frequency, apparent frequency. General formula of frequency is F equals V by lambda. Apparent frequency is F dash equals V by lambda dash, where V is the velocity of sound in air. So F dash gives V by V minus Vs in F, so many hertz. So the person standing on the railway platform will perceive the actual F hertz with V over V minus Vs into F hertz. Now, by deriving the Doppler's effect, we make some assumption. One of the assumption is velocity of sound is always greater than velocity of source or velocity of observer. It need not be an assumption, it is a common sense. What is the actual value of velocity of sound? Around 330 meters per second. Is it? Can any train move at that speed? Or can any person walking, standing on the railway platform exceed this speed? No. So, velocity of sound is always greater than velocity of source or velocity of observer in the Doppler effect. So, if you observe that in this formula, this V over V minus Vs should be always greater than 1, because velocity of sound is the biggest. Are you able to make it out? V is in the numerator, numerator is bigger or denominator is bigger? Numerator is bigger than denominator. Therefore, quotient should be bigger than 1. Since b by b minus bs is bigger than 1, it follows that f dash should be greater than f. When the source is coming towards the stationary observer. That is why the person standing on the railway platform perceives with greater frequency, because f dash is the apparent frequency is greater than actual frequency. If the train blows the horn at 540 Hertz, a person on the railway platform perceives at 560 Hertz. F dash is greater than f. If the source is moving away from the observer, in this case you see the source is moving towards the observer. Can you see that? Source is moving towards the observer. Supposing the source moves away from the observer like this. In that case, nothing to worry. Then f dash is given by d by d plus ds into f. Just make this ds negative, becomes positive on the other side. Okay. Now I write when the source moves away from the observer. You are on the railway platform and the train is going away from you. When the source moves away from the observer, then what is the actual frequency? What is the apparent frequency? You have to just change the sign of ds, negative ds to positive ds. Now here, v by v plus ds is a quantity which is less than 1, because denominator is bigger than the numerator. It is v plus ds, whereas numerator is just v. So therefore f dash is less than f. That means the apparent frequency as perceived by the person is less than the actual frequency. When the source moves away from the observer. When the source moves away from the observer receives at lesser value. F dash is less than f. So this is the first case. What is the first case of the Doppler's effect? Observer is in rest and source is moving. The source is in motion. So two formulas will come to us now. F dash equals d by d minus ds into f. When the source is coming towards the observer, stationary observer. Here also the observer is stationary. The source is only moving, but it is moving away from the stationary observer. In that case, this is the formula. As it comes towards the observer, f dash is greater than f, high frequency zone, and when it moves away from the observer, f dash is less than f, that means low frequency zone. So in this region, the wavelengths are much bigger. Here, wavelength is smaller. Many waves get compressed. Are you getting the basic idea of this Doppler's effect? Or Doppler is from Austin, or whatever I'm talking is like French and Latin and Austin to you. Are you understanding? So that's about Doppler effect of case number 1. Now we go to the next case. Now write, when the source is at rest, and observer is moving. When the source is at rest, the observer is moving. So at the beginning, both of them are at rest. Always Doppler's effect is considered that both of them are at rest. And then one starts moving either towards or away. Don't be under the impression that in the starting itself both of them are moving. When I say source is at rest, observer moving means initially observer also at rest, then he started moving. Are you following? So any basic situation is that both of them will be at rest. Then understanding the basic situation, then you have to make one to move either towards the other or away from the other. That depends. Okay. Now this is the source, and here is the observer. Now both of them are at rest. Okay. Now the source gives out some sound. It starts emanating. Emanating means sending off. It starts sending some sound, certain frequency, let's say F. The observer, he listens, and after he listens, the waves go like this. Now, the next situation is let the observer who was at O start moving to some distance, O dash. He was here. The source is not moving, it is at rest now. The observer is now moving. How he is moving? He is moving towards the source or away from the source? He is moving away from the source. With a velocity VO. He starts moving away from the source with a velocity VO, covering a distance OO dash in 1 second. That means velocity is equal to distance. Let S be the stationary source. Let S be the stationary source and O be the observer. And O be the observer. Let the source S emanate means send out F number of waves. F number of waves. That means it sends out some waves and that should have some frequency, and that frequency we are giving it as F. F number of waves. Let the observer at O move to O dash with a velocity VO in 1 second. In 1 second. Okay. Now here you have to observe one thing. In the region, say O to A, this much of waves were per second. Now he has started moving from here to here. Now he is moving away. He is moving away, right? So they don't get compressed now as in the previous case. As he comes to this region, it is only the wave that is present here will start coming into picture. So this region will have different frequency and this will have different frequency. You have to understand this point very clearly. Imagine the person is moving, this is the person, this is the source. Both of them were at rest beginning. Now this gave a siren, and from the observer who was there. I have not shown here anything, but that is not of no use for us. We are now talking about the sound that is perceived from the observer. You may be wondering that I have not written anything here. How is this wave starting from here itself? It's not like that. Would have come here also. But here, who is the point of action? Observer. So there is no point in showing the waves coming to the observer. From observer, since observer starts moving here, I have taken the wave starting from O, that's all. So this gives siren. The waves reach the observer, that is unwanted waves for us. But once it reaches the observer, now the wave continues to move with a certain frequency. Now imagine the observer is moving like this. He moves from O to O dash. Since he is moving away from the source, there is no question of waves getting compressed here. Rather than this region, this portion of the waves will not reach the observer's ear. As he moves from O to O dash with the velocity V naught, this portion of the waves or the frequency, this particular frequency from O to O dash will not reach the observer's ear, and he will start receiving or perceiving the frequency what is there left from O to A, that's all. Okay? Now, what is the frequency from O to O dash? What is the basic formula for frequency? F equals V by lambda. Okay? Did you write this diagram? Did you write this statement also? Okay, fine. Now you write. The observer will not receive the frequency from O to O dash, but he receives only the frequency F minus V naught by lambda. This is not V naught, it is actually VO, velocity of the source. Receives the frequency F minus VO by lambda in the region O to A. Now I will explain what is this. What is the total wave from O to A? F. Now what is the base from here to here, O to A? O to A should be F. But the observer is not hearing to the waves from O to O dash. That frequency he will not listen. So how much he should be left with? This entire is F minus whatever the frequency that was there from O to O dash. What is the formula for frequency? F is equal to V by lambda. Right? So from here to here, V is same as distance because it is again 1 second. So F equals, instead of velocity, this is V naught divided by lambda. Did you understand? Did you understand this rotation? V naught by lambda. Yes or no? Because the observer moves with the velocity V naught in 1 second time. So the frequency from O to O dash, what is the frequency? I write frequency is velocity of the observer divided by the wavelength, that is from here to here. entire is how much? F. Here to here is how much? V naught by lambda. So here to here is how much? F minus V naught by lambda. What is this F minus V naught by lambda? It is the frequency that the person who has moved from O to O dash starts perceiving. So it is actual frequency or apparent frequency? Apparent frequency. So we can say F dash. F dash equals F minus V naught divided by lambda. So the entire discussion goes like this. There is a source S at rest and there is an observer O. The S source gives out sound of frequency F. So I start counting it from as it reaches O. So what is, how many number of waves are contained from O to A? F number of waves are contained from O to A. As the person starts moving from O to O dash, since he is moving away from the source, there is no compression here. Then what happens? The person will not perceive the waves that are present from O to O dash. What is the frequency of waves that are present from O to O dash? V naught by lambda, and V naught is the velocity of the observer. So he is able to now perceive only the waves that are in the region O to A. How many waves are now left out in the region O to A? F minus V naught by lambda. So these are the waves that he is going to perceive, means it is apparent waves, not actual waves. So that should be F dash. So F dash equals F minus V naught by lambda. This is the situation. Now see this. I can replace 1 by lambda. See here, lambda is V by F. So 1 by lambda is how much? F by lambda. Take the reciprocal of it. Now just look at the board. So F dash equals F minus, I keep this V naught as it is. There is 1 by lambda is there. 1 by lambda is there. I write it as F by V. Or F is common factor, 1 minus V naught by V. Or F into, take LCM, V is LCM, V minus V naught. Therefore, I get the final formula for the apparent frequency when the observer moves away from the stationary source as V minus V naught divided by V times F. So many terms. Remember, the apparent frequency that the observer listens when he moves away from a stationary source, producing an actual frequency of F waves, is velocity of A, velocity of sound in A, minus velocity of the observer divided by velocity of sound in A into the actual frequency emanated. This is the apparent frequency that he gets on. Now tell me whether numerator is bigger or denominator is bigger. Denominator is bigger. So this ratio should be less than 1. So this implies, since V minus V naught by V is less than 1, implies F apparent is less than F. So when the person moves away from the stationary source, how the apparent frequency, it is greater or lesser? Lesser than the actual. F dash means apparent. Apparent is lesser than the actual frequency. Okay? Now on the context, let's also talk about the observer, instead of moving away from the source, starts moving towards the source. I am now talking about the next possible situation. if the observer moves towards the source, towards means he is now in compressed region, lesser wavelength, larger frequency area, high frequency area, then what is the formula? F dash equals V plus V naught. Just have to make the sign positive. Now tell me whether numerator is bigger or denominator is bigger. Numerator. Therefore, the ratio V plus V naught by V is bigger than 1. So this implies F apparent is greater than F actual, because he is in high frequency area. He is in high frequency area. So this is about the Doppler's formula for the source at rest. The observer is moving either away from the source or towards the source. Understood? Understood? Yes. Now we have the last case. When both observer and the source are moving. Okay. What is the first case? What is the first case that we discussed? Who was at rest? Observer was at rest and source was moving towards the observer. Now this is very simple. Third case is very simple. We just combine both the results, that's all. We know that when the source moves towards the stationary observer, then what is the apparent frequency? Engine is coming towards the person in the platform. F dash equals first case, F dash equals V by V minus Vs. V divided by V minus Vs into F. That is the actual frequency. Now see that source moves means you should take the velocity of source. Vs term. Also we know that when the observer moves, away from a stationary source, then what is the formula? F dash equals V plus V naught divided by V. This is V minus V naught or V minus V. If you write plus, what happens? Observer is moving towards the source and return away from the source. So it is minus. Remember, in all away situation type of formulas, the velocity of the source or the velocity of the observer will be minus. In all towards kind of situation, V naught and VO will be, VO and VS will be plus. It's very easy to remember. Okay. Now, let us connect both these formulae. Or I will just write it as F2 dash equals, instead of one single dash, I write F2 dash equals F dash, instead of simply writing F, I write V minus V naught by V. Write all these formula as 1 and this as 2. Now what is the situation I am talking about? Case 3. What is case 3? When both of them are moving. Here one is moving. Here another is moving. If I combine both are moving. isn't it? So in order to develop a relationship between the two, I just make a small change in the notation. Write it as F2 dash equals F dash V minus V naught by V. So to combine these two, for F dash, in place of F dash, you substitute this value. You will get the final form. You catch my point? Yes. Now, from equations 1 and 2, from equations 1 and 2, from equations 1 and 2, F2 dash equals, for F dash what should I write? V by V minus Vs into F. V by V minus Vs F into V minus V naught by V. Okay, you understood? Combining both. I just combine both the equations. Put in place of F dash here, put this value. So you cancel this V and V. So F2 dash equals, when both are moving, the apparent frequency comes out as V minus V naught divided by V minus Vs into F. Okay. Now here we have 4 types of situations. Substitutions like this. One is the source, other is the observer. This is source, this is observer. This is observer is both are moving. Source is also moving, observer is also moving. Can you see this? Both are moving. The train is going, passenger is running behind the train to catch the train. Both of them are moving in the same direction, right? The observer and source, again they are going in the same direction, opposite. Person is running, train is chasing. Okay? Or, see, I am talking about, these are the examples, I said 4 cases where both are in relative motion. Or, person is coming, train is also coming. Dangerous situation. Both of them are head on. That means both of them are moving towards each other. Or person says your train is not good, train goes off, person goes off. Did you analyze the 4 situations? So that 4 situations can be obtained by altering the signs. Here both are negative. If both are negative, is it away or far? Like this. They are going like this now. Now if I make both plus, if I make only this plus and this negative, observer is coming towards the train. And this plus and this minus, 4 situations. You get the respective formulas. Okay? Now, if an extension I am talking about, V naught equals Vs. Let's suppose that the velocity of the source and the velocity of the observer are same. Can you give an example how, when this is possible? Okay, no, not even that way. You are sitting in a train and the train is going, he is blowing the horn. If train moves at 50 kilometers per hour, can the person in the train move at 100 kilometers per hour? If the engine moves at 50 kilometers, you also have to go at the same 50 kilometers, the same direction. So, velocity of the observer and velocity of the train is also same. You don't experience Doppler's effect if you are sitting inside the train. You are sitting in a train from opposite direction, one more train comes, you experience. With the same train you don't experience. You don't get that Doppler's effect, you don't get that sirening. What is that sirening? That type of effect you don't get if you are sitting inside the train. You listen to the actual horn, not special horns, right? This is because if V naught equals Vs, now what happens? I put Vs here. this gets cancelled, right? If V0 equals Vs, then F2 dash equals F. That means F2 dash minus F equals 0. That is, apparent frequency becomes actual frequency. There is no change in the frequencies. Apparent is actual. So that is why a person sitting in the same train will not experience Doppler's effect. Doppler's effect is experienced only for a person standing on a platform, not for the person sitting in the train, same train. He doesn't experience Doppler's effect. Okay? Now, where do you apply this Doppler's effect? Doppler's effect is applied to limit the speed of the vehicles. Now, overspeeding vehicles, they are caught by police by using the phenomenon. The principle they use is Doppler's effect. They assign a certain speed. The car should come at 80 kilometers per hour. That's the maximum speed limit. Supposing the driver touches 110 kilometers per hour. You know, there is a change in the frequency. When he blows the horn, the frequency change is reflected in high frequency area. Up to 80 kilometers per hour, it is normal frequency area. That is what police have declared. Let's assume. If the person drives the car in that area with 120 kilometers per hour, then what? He is creating more frequency. The waves generated that are in front of him will have more frequency, less wavelength. So this change he created because of his overspeed. If he had come at 80 kilometers per hour, then he wouldn't have created any changes. All the changes that he would have created have been accepted. If 120 means you are increasing the frequency of that zone still higher, and that will be received by the sensors, so you are punishable. So what is the use of Doppler's effect? Overspeeding, to stop overspeeding of vehicles. Number 2, you can detect the submarines, enemy submarines, and find out at what distance they are. For that also Doppler's effect is used. And Doppler's effect is also used to establish the distance between stars. Two stars are situated at what distance, and so on. And Doppler's effect is also used in spectroscopy and in redshift. You know what is redshift? That shows that the universe is continuously growing. And these are some of the applications of Doppler's effect. Okay? So now we have to do workout problems on Doppler's effect.